Okay, let's get started. Welcome to lecture 7 of the planets. The moon has gone around the Earth almost one complete revolution during this semester already, not quite. And we're going to talk a little bit today about the moon and how the moon and the sun create tides here on the Earth, and indeed how the Earth creates tides on the moon. We're going to talk about the difference between mass and weight, something that comes up in your homework. And then the last 2/3 of the lecture are going to be about some very important fundamental quantities that bear on our daily lives, and certainly in the realm of physics, namely energy, momentum, and angular momentum. So let's get started. There's homework due tomorrow. A lot of what I lecture on right now comes up in that homework. If you haven't had a chance to relax and read chapter 4, you should definitely do so. For the rest of your life, you'll remember the physics that is the essence of chapter 4. Now, there's one confusing topic that we didn't cover last time, which is that I mentioned this stuff called mass. What is mass? It comes up in Newton's law that says force equals mass times acceleration. The acceleration of an object is equal to the force exerted on it divided by the mass, solving for the acceleration. And moreover, in Newton's law of gravity, remember that both masses, m1 and m2, that are attracted to each other, come into that formula for gravity symmetrically. But we didn't really define what mass is. It's a rather peculiar and mysterious quantity. And moreover, what's the difference between mass and weight that you measure when you step on a scale? Well, here's the answer. Mass is the amount of matter in an object. I like to think of it as simply the number of atoms in an object multiplied by the mass of each one of the atoms. Every atom that you see on the periodic table over here has a mass. It's even listed here. And every object that we know of, whether it's your human body, a car, a computer, the planet Earth, the air, consists of atoms. And each atom has a certain mass. If you add up all the masses of all the atoms, that's your total mass. It doesn't matter what planet you're on, whether you're in a spaceship or on the moon. The mass is the same because it's simply the amount of atoms and their respective masses. And mass comes in, as I said, in a very peculiar way in this major equation from Isaac Newton, that force is equal to mass times acceleration, or in other words, the acceleration of an object as it speeds up, increases its velocity, is equal to the force exerted on it divided by the mass. So mass in some way is simply a quantity that resists acceleration. The more the mass of something, the less it will accelerate when you push on it. If you push on a small object, like let's say a piece of chalk, if you push on this with a certain force, the chalk goes shooting out. If instead you push with the same force on a truck, the truck hardly budges. And if you push on the planet Earth with the same force, the Earth hardly budges, because its resistance to acceleration, namely the mass, is so large. So that's mass. In contrast, weight is a word that simply means the force due to gravity. So every day in your lives, you live on the planet Earth, you have a certain mass, but there's a gravitational force pulling you downward due to the Earth, of course. And weight is nothing more than the gravitational force on you due to whatever gravitational field is in your vicinity. It might be the planet Earth or the moon or whatever. Maybe there's no force on you at all. So weight is a force, whereas mass is simply the amount of material. Okay? And you can compute the gravitational force on anything, again using force equals mass times acceleration. But in the case of weight, force equals mass times, well, the acceleration of any object near the surface of the Earth is this quantity little g, the acceleration of an object when you drop it. So if you have some kind of an object with mass and you drop it, missed my iPhone by that much. The ball accelerates downward with an acceleration little g, 9.8 meters per second squared. So the weight of an object is the force on it due to gravity. And there's a number of examples of this in your daily life. You all look with trepidation at the scale to see how much gravitational force you've gained by eating too much. And of course, you all know that on the moon, the force of gravity is lower. So you can jump higher when you're on the moon. And so you could ask, you know, what is your mass on the moon? And more profoundly, you could ask, what is your weight on the moon? And so as a quiz question, you can get out your colored pieces of paper early. I have a lot of questions today. Here are 4 possibilities, and I'd like you to pick which one is right. If you go to the moon, my weight is the same, my mass is less than it is on the Earth. B, my weight is less, but my mass is the same. C, my weight is more, my mass is the same. And D, my weight is more and my mass is less. So you can show me your colored cards right now. And many of you have the letter B out. That's correct. Your weight is less on the moon because the gravitational force on you is less. If you could put a scale on the moon and step on it, you'd weigh 1/6 as much as you do here on the Earth, because the gravitational acceleration, the gravitational force is 1/6 on the moon that it is here on the Earth. There's an interesting thought experiment you can do by comparing mass and weight when you're in an elevator. Some of you may have noticed that something funny happens when you're in an elevator and it starts going up. You feel something funny in your legs. And when the elevator starts going down, you feel something funny. So when you're in an elevator, you could next time bring a scale and actually measure how much you weigh in the elevator. And when it's stationary, you weigh whatever you weigh. And again, I'll remind you, the units of weight, which is a force, in English units are pounds. A little bit ugly, because in the metric system, they are newtons. Force has units of newtons, appropriately. But now, what about an elevator that is accelerating upward? Just when you start, you get in an elevator and you press 28 to go to floor 28, the elevator starts accelerating upward, and I bet many of you have experienced what I have, which is as soon as the elevator starts going up, you feel like you have to brace yourself a little bit. And indeed, if you had a scale and you stood on it, you would notice that you weigh a little bit more. Not the 135 here, but something closer to 145, let's say. So in fact, there's a little more weight that you have due to your accelerating frame of reference. A very profound point, by the way. And similarly, when the elevator begins accelerating downward from a top floor, you all know that momentarily you feel a little lighter. If you were on a scale, you would weigh less. The amount of force you have to push on the ground to stay upright is less. And of course, the force with which you push down on the ground is exactly the force you need to remain stationary relative to the elevator. So there's an accelerating frame of reference when you're in an elevator, either up or down, and that causes something odd to happen with regard to your weight as measured by a scale. And most profoundly at all, what if the cable breaks when you're in an elevator? You're in an elevator, the cable breaks, and suddenly you are in free fall. You would be in the elevator, and for a while you would just be floating like an astronaut in the space station. You'd literally be just floating in that elevator. Why? Because the elevator is accelerating downward at 9.8 meters per second squared, and your body, would be accelerating downward at 9.8 meters per second squared. You're both going down at the same speed, and you could just be floating in that elevator. In effect, you're weightless. And it's rather a profound issue that the weightlessness that you would clearly experience, any experiment you did in that elevator would prove that you were weightless, is the same as if you were in outer space, millions of light years away from the Earth and the Sun, floating in outer space in a box. That would be the same as what you would feel in this elevator. There's no difference between being in free fall in a gravitational field and being very far from any gravity at all. And it's one of the most profound equivalences in physics. Being in a strong strong gravitational field, but free falling is the same as being in outer space. Now, this happens, of course, for the astronauts. When they go to the space station, they, of course, have their same mass. Their body still has the same number of atoms. But in outer space, when you're orbiting the Earth, let's say, you're in the space station orbiting the Earth, you all know that the astronauts feel weightless. And that weightlessness is due to the fact that they are like in an elevator. They are falling in the shuttle or the space station, continuously orbiting the Earth, falling toward the Earth, but their tangential sideways horizontal velocity keeps them curving around the Earth even though they're falling toward the Earth. So the weightlessness that the astronauts experience is ironic because, of course, they're in a gravitational field. Otherwise, they would fly off and they wouldn't be attached to the Earth at all in an orbit. So even though they're in a gravitational field orbiting the Earth, they feel weightless because they're free falling, as you would in an elevator. So there's some very profound issues. What, in fact, is the difference between free falling in a gravitational field and being very, very far away from any gravity at all? They seem equivalent. And in fact, you can't tell the difference. And when Einstein realized this back around 1905, he realized there must be something wrong with Newton's formulation of gravity. Somehow or other, free falling and no gravity at all are one and the same. And Einstein figured out a way to indeed incorporate both of them into a self-consistent theory that, in a way, is much more sophisticated than Isaac Newton's laws of physics. Okay, turn over a new page in your brain. We're going to talk for a few minutes about tides. I love tides. I love going to the beach, and as soon as I get to the beach, I quickly look at the sand, and I look to see, is the sand wet? Because if the sand is wet, I know that the ocean tide brought the water up to that sand maybe an hour or several hours ago, but now the sand is exposed, wet, and the tide is out, has carried the water out. Other times I go to the beach, and I bet all of you have had this experience too, and you see the water is up high, and there's no wet sand and no wet rocks, and you know it's high tide. And you know that at certain times of the day you have high tide, and other times of the day you have low tide. And I'd like to talk a little bit about how that happens. So if you're lucky, or if you're smart, you will someday go to the far eastern reaches of Canada. And there is a bay, a large bay, called the Bay of Fundy. And I went there specifically just to see the tides. And here's a picture of the Bay of Fundy, and there's a boat at the dock. At high tide, 6 hours later, here's what it looked like. They have some serious tides there at the Bay of Fundy. 15 feet common difference between high tide and low tide. And every 6 hours it switches from high to low and then back to high and on and on and on. So the tides are remarkable, and if you watch for a day, you'll quickly verify what all of you know. Every day there are 2 high tides and 2 low tides. Why? Why is something as fundamental as tides so reliable, like a clock? And is it exactly 6 hours, or is it 6 hours and a little smidgen more or less? Well, you can do the experiment yourself by walking on the beach. There's clearly low tide. There's another low tide there. You can watch for a while and see how long it takes the high tide to switch to a low tide. Here's a little video of the Bay of Fundy, since as you can tell, I like both tides and the Bay of Fundy. Mostly I like saying the word Fundy. That's pretty cool, and you can go to the Bay of Fundy and see this happen all the time. And it is kind of scary like that too, because you wonder if you're going to get trapped by the water coming in. So it's pretty exciting. We have tides, of course, in the Pacific Ocean, the Atlantic Ocean, the Indian Ocean. Here are the tides for today, September 18th. This is today. And if you go out to the bay or to the Pacific Ocean right now, there was a low tide at around 2:18 a.m., another low tide this afternoon at 2:29 p.m. There was a high tide at around 9:30, and then another high tide will happen later this evening at 8:22 p.m. So here again, 2 high tides and 2 low tides happens every day. And by the way, one thing that you would notice if you were just a little bit observant is that the low tides always happen as the moon is rising in the east or setting in the west. The moon rising or the moon setting is roughly within a half an hour or so the time that you get low tides. And when the moon is overhead, you get a high tide. And 12 hours later, when the moon is beneath your feet, you also get a high tide. So the moon is clearly the culprit here. Any detective would catch that. And you could even track day after day, hour after hour, day after day, track the tides during a whole month. And here's what your graph would show for the tides during a month. High and low and high and low and high and low, twice per day for an entire month. Yeah, it's curious. Some days the high tides are higher and the low tides are lower, and other days the high tides are not so high and the low tides not so low. And there's some kind of periodicity here, which, by the way, seems to have a period of about 1 month. You see it goes high and then low and then high again, and at the end of 30 days, you're back to where you began. So there's some other periodicity that's not daily, but monthly, and that's another clue. This must have something to do with the moon, because the moon takes about 1 month to go around the Earth. By the way, all of you know, probably, that the origin of the word month is moon. 30 days is 1 month. So why is it that we have 2 high tides, 2 low tides, and they're separated by a little more than 6 hours from high to low and then back to high again? And why do the amplitudes of the highs and the lows change during a month? Well, the answer is surely something about the moon, and the only way that the moon affects the Earth is gravitationally. And so we could look then at a sort of a sketch of how the gravity of the moon acts on the Earth. And here's a diagram. I'm going to show you several of these because this is one of the most important concepts in this whole course, and it's not that easy to get. There's the moon, there's the Earth. You could ask, what's the gravitational pull of the moon on the nearby water on the ocean? And if you were a gram of water on the near side, you would feel a very strong force on you as a gram of water because the moon is close to you. If you were a gram of material in the center of the Earth, you would feel a weaker gravitational force on you due to the moon, shown by this arrow. And if you were a gram of water on the far side of the moon, you're so far away from the moon that you would feel a weaker force. And so the Earth gets stretched out. The side closest to the moon gets pulled toward the moon strongly. The middle of the Earth pulled toward the moon less. The far side of the Earth over here gets pulled less still. And so the whole Earth gets sort of stretched out. It's very much like pulling it from one end to the other. And so the key to tides is that the moon's gravity pulls on the ocean more strongly on the near side and less strongly on the far side, and the middle of the Earth feels an intermediate force. And that's what causes the tides. Moreover, we have left out the sun. Does the sun cause tides on the Earth? Well, there are 2 counteracting ideas here that all of you can imagine. The sun is much farther away than the moon is. And so you might think the gravitational force exerted by the sun on the Earth is weaker because the sun is so far away, and that's true. Remember, the gravitational force is proportional to 1 over distance squared, and the distance to the sun is 93 million miles. Moon is only 250,000 miles. On the other hand, the sun is a whopping massive object. The sun has a mass that's far greater than that of the moon by a factor of about 10 million or so, maybe 100 million. And so even though the sun is farther away from us, it's more massive, and it must exert a stronger gravitational force to make up for its great distance. And so the sun actually matters. The sun does cause tides, but only about a third as strong as the tides caused by the moon. So the sun and the moon together cause tides, the sun a little less important. And so you get two types of tides. When the sun and the moon line up with each other, you get strong tides, sometimes called spring tides. And when the moon is oriented 90 degrees between the moon, earth, and sun, then the moon is pulling the tides up toward it, but the sun is pulling the tides in the perpendicular 90 degree away direction. And so they sort of cancel each other a little bit. There's still high tides. Why? Because the moon dominates and gives you a weaker high tide, called a neap tide. So that's why the tides have high highs and sometimes not so high highs. It depends on whether the moon and the sun are aligned with each other. And by the way, it doesn't matter if the moon's on the other side, because if the moon's on the other side, you still get two bulges, and the sun is helping even though it's on the other side. And I'll show an example of this in a second. Yeah.
So the neap tide is like a low high tide?
Yeah, so the neap tide is like a lowish high tide. Yeah. Here's a few more examples. I couldn't understand a thing he was saying. If he would only speak English, then I would have gotten it. That's my complaint. Here's yet one more video that shows how this all works. There's a little animation. You're going to see the moon orbit the Earth and pull the tides along with it. So you see the moon orbiting the Earth spinning on its axis once per day, and the tidal bulge always points roughly toward the moon and away from the moon, but not exactly. Why? Because the Earth is spinning, rubbing under the ocean, and the Earth spinning pulls the water a little bit ahead of the moon. Not much, but just a little bit. So the tidal bulge points almost toward the moon, but a little bit ahead. And that has the very interesting consequence that the moon is going to pull back on the bulge here a little bit. So the moon is actually causing the Earth to feel what's called a torque, pulling the Earth backward a little bit, and in turn yanking the moon forward a little bit. The fact that this bulge is ahead of the moon means the moon's getting pulled forward, the Earth's getting pulled backward, slowing down the spin rate of the Earth. And over the course of centuries and millennia, the spin of the Earth is slowing down. So it's very interesting, and the moon is getting energy, getting spun up. Wild. So those are tides. You should have noticed, by the way, that when the moon and the sun were lined up, you got high tides, and when the sun and the moon are 90 degrees to each other, you got less high tides. Okay. So here's a quiz. This is a good quiz. This is the kind of question that I hate to say it. Okay, I'll say it anyway. It's the kind of question I like to put on a midterm. Here it is. Today, we're just a little bit past last quarter moon. It was a quarter moon a day or so ago. And so you just to imagine this to make it a little easier, suppose it's a quarter moon right now. By last quarter moon, remember what that means is that we're heading toward new moon. And in fact, we'll be at new moon in about 3 or 4 days. So given that we're at last quarter moon, let's say, what times will the tide be high here in San Francisco? You might want to give this a little bit of thought. If it's a quarter moon, when will the high tides occur? There's 4 possible answers. I'll give you 10 seconds to think about it. All right, well, show me your answers. I guess you might want to show two colors since there's only two pairs of answers. I see a lot of BDs and ACs. Maybe more ACs than BDs, but it's a close call. So let me tell you how I work this out. I don't know the answer to this question, so let me open my brain to you so that you can see how I would think about this. I know that our class starts at 5 p.m. And when we walk outside at the end of class, it'll be 6:30 p.m. And I know that the sun is going to set maybe an hour after class or 45 minutes, something around 7 p.m. or a little earlier. So by the time we walk out of class right now, I'm going to walk out of Pimentel, and I'm going to walk out that door, and I know I'm going to be facing west toward the bay, toward the Pacific Ocean, toward San Francisco. And I know that I'm going to see the sun just barely above the horizon. Why? Because the sun is setting in the west. Now, if the sun is setting in the west as we walk out of Pimentel at 6:30 p.m., which is close to 7 p.m., where will the moon be? That determines the tides. Well, I struggle to figure this out. If the moon is setting, if it were a full moon, the moon would be opposite the sun. But it's not a full moon, it's a quarter moon. So that means the moon, if the sun is setting, the moon must be either overhead, 90 degrees away from the sun, so that it looks like it's cut in half, like a good self-respecting quarter moon, or the moon is beneath my feet, in which case the angle between the moon and the sun setting is also 90 degrees. So I think I'm a little confused, or at least I'm pretending to be confused, that if the sun is setting in the west, the moon must be either overhead or beneath my feet. Now, I can take this a little bit farther just to let you know. I know the moon goes around the Earth counterclockwise. So if I see the moon in the west when I walk out of Pimentel, the moon in its orbit around the Earth is going to go counterclockwise around like this. And so I actually think if the moon were overhead, that would be a first quarter moon heading toward full moon. So instead, the moon must be beneath my feet. That's fine. When we walk out of Pimentel, you'll see the sun setting, I presume, and you'll know that the moon literally is beneath your feet, somewhere down there somewhere. Now, if that's true, that the moon is beneath your feet, it's going to produce a tidal bulge down there at China, and also a tidal bulge opposite the moon here in the Bay Area. So it'll be a high tide. So I think the high tide is going to occur around 7 p.m., just based on that logic. And then obviously, if there's a high tide at 7 p.m., there must have been another one at 7 a.m. Now, where did I go a little bit wrong? Well, we're not at quarter moon. We're a little past quarter moon, and the moon goes counterclockwise. So it's going to rise on the eastern horizon a little later, maybe an hour or two later than we had imagined in our quick explanation. So I think 7 p.m. and 7 a.m. are not quite right. It's going to be a little later, maybe 8 p.m. and 8 a.m., or maybe even 9 p.m. and 9 a.m. And so that's how you can do the problem. Imagine where the sun is, and therefore where the moon must be to be a quarter moon, and therefore what the tide must be. 7 a.m. and 7 p.m. would be the best guesses, but I already told you the answer because I showed you the tide table for today. So remember what it looked like. Here it is. Remember that high tide was at 9 a.m., not 7 a.m., and 8:22 p.m., not 7 p.m. As I had mentioned, a little later, because the moon has gone a little past quarter moon, and so the tides are high and low, a little later than we had guessed from our simple perspective. Notice how we solved the problem, and then we made a little correction to our answer based on a little extra information. that the moon had orbited a little farther around than just a mere quarter moon. And you know, the overarching idea in my explanation here is that you can figure things out. All of you can figure things out. You just have to kind of go step by step. What do you know? What's the picture? Maybe sketch it on a piece of paper and slowly but surely piece together a good solution to your problem. There's your tides again that actually happened today. Okay. Unfortunately, there's yet one more fly in the ointment. And that fly in the ointment is that when there's a high tide, the water fills up the ocean basins, Pacific, Atlantic, wherever you happen to be. But if there's a bay, it takes a little while for the water to flow into that bay. Water doesn't flow instantly. And so the high tide in the San Francisco Bay occurs with a little delay of about an hour or maybe an hour and a half. If you go to Angel Island on the ferry, which all of you should do, or if you go to Alcatraz, the tides occur a little later there because the water had to flow in through the Golden Gate from the Pacific Ocean, and so the high tides are lagging and the low tides are lagging what they normally do. One last note that I've already mentioned, the moon yanks on the Earth. And it yanks on the Earth, causing it to spin backwards. That is to say, the moon pulls on the bulge here, pulling it toward the moon, slowing the Earth's rotation, because this bulge is getting yanked back toward the moon. So slowly but surely, tides between the moon and the Earth are slowing the spin down of the Earth and spinning up the orbit of the moon. Okay. Now I want to change topics to talk about energy. In your lifetimes, for the next 50, 60, 70, 80, 90 years, energy is going to be a topic that's important to all of us in our daily lives. We need energy to run civilization. And so it's very important to understand what is energy, what are the different types of energy, and how can you perhaps transform one type of energy into another type that you need. For example, airplanes. Airplanes are propelled by liquid fuel, fossil fuels, gasoline. And it's hard to imagine that airplanes are going to ever operate on any other type of energy. Solar energy is not enough to make an airplane go. Batteries aren't efficient enough to make an airplane go. So energy is a complicated issue, and you need the right form of energy to have the energy perform the task that you want. So let me review for you the types of energy there are. All of you know a lot about this already. There's kinetic energy, that's the energy of motion. There's potential energy, that's the energy that happens when you take a massive object like this rock and you push it upwards. You did work, and now this object has potential energy. Why do we call it potential energy? Because it has the potential to adopt and take on kinetic energy. Potential energy converted to kinetic energy. Potential has the potential to create kinetic. There's thermal energy. I'll show you what I mean by heat or thermal energy. There's chemical energy. That's what allows gasoline to work, or a battery. The bonds in atoms create a type of bound energy. There is, of course, nuclear energy. The nuclei of atoms, the protons and the neutrons in the nuclei of all of the atoms here, those protons and neutrons are bound to each other and have a certain amount of energy that you can release by engaging in nuclear reactions. There's, of course, also light. Light has energy, and we'll talk about that next week in spades. We'll talk about how light carries energy and how you can make use of light as energy. One side note is that mass and energy can change from one to the other, and only Einstein figured this out. It turns out that mass and energy are really two forms of the same thing, and it's so profound that I'm not going to say much more about it, but the famous equation E equals mc squared says that energy can convert into mass, with c being the speed of light. And we'll talk about that more a little bit later too. For all intents and purposes in your life, energy is always conserved. You can't create energy, you can't destroy energy. All you can do is change the form that the energy is in: kinetic, potential, chemical, light, and so on. Energy is conserved. So what are these different types of energy? Well, there's kinetic energy. You might have learned about it in high school. I'll remind you, kinetic energy is the energy of something moving. And there's an equation for it that's very simple, it's powerful. Kinetic energy is 1/2 times the mass of an object times the square of the speed, or the velocity of the object. 1/2 mv squared is the amount of kinetic energy anything has, whether it's a rock, a truck, or a planet. Here it is again, kinetic energy, 1/2 mv squared. You can always figure out the kinetic energy of anything if you know its mass and its speed. Now, you can create kinetic energy if you have potential energy. And as I just mentioned, one way to get potential energy is to take a massive object and lift it up so that it now has potential energy. If you lift a ball up a height as shown here, then there's an equation for the potential energy that something has, and that equation is the mass of the ball or the object times little g, the gravitational acceleration on the Earth, 9.8 meters per second, times the height that you've raised the ball. mgh is the equation for potential energy. Do I care much about equations? Nope, not really. But you should realize that the height here matters. If you take your ball and you lift it a certain height, the higher you lift it, the more potential energy it has. If you're riding a bicycle and you ride your bike up to the top of a mountain, you've gained potential energy by your own work, your hard work riding your bike up the mountain, and the height of that mountain is proportional to how much potential energy you have with your bike up that mountain. And moreover, the amount of mass that you lifted up there is also proportional to the potential energy. The more mass and the more height that you've lifted something, the more potential energy you have. And you can convert that potential energy into kinetic energy by dropping the ball. When you drop it, it gains kinetic energy. And when it hits the ground, how much kinetic energy does it have? 1/2 mv squared? Well, it has an amount of kinetic energy equal to the amount of potential energy that you put into the system to begin with. Because energy is conserved, you can't create or destroy it. If you created potential energy, all of it must get converted into kinetic energy when the ball finally ends up back where it started. Okay? By the way, when the ball hits the ground and thuds and comes to a stop, its kinetic energy is 0 and its potential energy is 0. So where did the energy go? Something's fishy. And the answer is, when you drop a massive object on the ground, it loses its potential energy. It gained kinetic energy momentarily, but now that's gone. So the ball actually delivered kinetic energy to the ground, and the atoms of which the floor is composed are now jiggling around because those atoms got bumped by this ball that rammed into those atoms, and now the atoms have the energy that was originally potential energy. So the energy has to go somewhere. Atoms jiggling around, by the way, on the floor is called heat. Okay, here's some more examples. When you ride your bike, you actually put energy in by riding the bike. You gain kinetic energy when you ride it. When you get to the top, you've converted that kinetic energy up to potential energy. And then if you ride down, it's kinetic energy again, and you're losing potential energy. So the potential energy, mgh, is conserved as you go up and down. And of course, this is exactly how a roller coaster works. Roller coaster, if you've ever been in a roller coaster car, you might have asked yourself, hey, where's the engine? By the way, where's the steering wheel? But where the heck is the engine? Well, there are no engines. Roller coaster cars have no engine. It's working by converting potential energy when you get up to the top, chugga, 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 and then you're just rolling down, converting your potential energy into kinetic energy. And so that's how a roller coaster works, of course. If you see that thing flying off, it has potential energy, and it's converting the potential into kinetic energy. That's all that's happening. On a frictionless surface, this happens easily. And all of you know this is how it works. So every time you go to an amusement park and you ride on a roller coaster, you should think about the physics experiment that you're a part of. And of course, there are other types of potential energy. When you use a bow and arrow, you're stretching the string that's the part of the bow, storing potential energy, and then when it springs forward, that potential energy of the bow gets converted into kinetic energy. And she knew that perfectly well. Indeed, in orbital motion, there's also potential and kinetic energy. When you have, let's say, a comet come in and go like that, as the comet sweeps into the sun, it has a lot of potential energy when it's far away, and the comet gains kinetic energy when it goes around the sun, and then as it sweeps back out far away, obeying Kepler's second law, it of course slows down, and it's now got less kinetic energy, but more and more potential energy. There's also heat energy. I mentioned it earlier when I said that you drop a ball and the kinetic energy gets converted into heat, heating up the atoms of the ground. The same thing happens when you throw a football or hit a tennis ball. The ball runs into the atoms that make up the air. And those poor unsuspecting atoms get blasted by the ball, and the atoms recoil because they just got hit by this football, and now the atoms are moving faster. They have kinetic energy. We call that heat. When atoms or molecules have a higher and higher velocity, we call that heat energy. It's of course nothing more than kinetic energy, and you can see that clearly here. Here's thermal energy. Here's a bunch of atoms hypothetically in a box, and each of the atoms of course has some velocity and therefore kinetic energy. And the sum of all their kinetic energies is what we call heat. So here's a box that has some heat energy, but you can see clearly with your own eyes that the heat energy is really composed of the individual kinetic energies of all of the atoms or molecules that are inside that box. There's another kind of potential energy, and that's the kind of potential energy that happens in a battery that powers an electrical device. In a battery, there's chemical potential energy, and that chemical potential energy pushes on the electrons, literally pushing on the electrons in the copper wire, making the electrons move, and they can go through a light bulb and make the light bulb light up, and go back into the battery. They've lost their energy by the time they make it back to the battery, but the battery boosts their energy again, and so the battery is the way that the electrons that make up the current in that wire, the battery is where the electrons get their energy to be powered around the loop. Okay? Now, I've mentioned this a couple of times, but now I want to emphasize it. In your daily lives, energy is always conserved. That's a fancy word to mean energy is never created or destroyed. If you get a little extra energy over here, it had to come from somewhere else. You can't create or destroy energy. So energy can change from one type of energy to another, one form to another, but the total amount of energy stays the same. And I'll tell you what I'm thinking in the back of my mind. I'm imagining a box. Inside that box, no matter what happens, there might be kinetic energy, potential energy, roller coasters, batteries. There could be mice running around on a little wheel. There could be food for the mouse to eat, and the mouse is using that food in some way to power itself and run on a treadmill and make some generator work which lights up a light bulb. Whatever is happening inside that box as energy transforms from food to the mouse, to the treadmill, to the light bulb, there's always the same amount of energy inside that box. It's converting from one type to another, but you're never changing the amount of energy within that box. It's an amazing conservation law. And by the way, this is pretty wacky. Just a second. Energy has lots of different forms: light, heat, potential, kinetic, electrical, chemical. But somehow it's conserved. It's like apples and oranges, but there's always the same total amount of apples and oranges. So energy is rather amazing. Yeah?
Does this apply prior to the Big Bang?
Is what?
Does this apply prior to the Big Bang?
Does
this apply prior to the Big Bang?
Is the energy supplied prior to the Big Bang?
Does it apply?
Oh, does it apply to the Big Bang? The question is, does energy conservation apply to the Big Bang? I don't know. And I'm saying that with some profound knowledge of what's going on. The Big Bang itself is mysterious. We'll talk about it later in the semester. And then what happens in the expansion of the universe after the Big Bang is also a fairly profound issue, because you might ask, is that expansion of the universe a type of kinetic energy? And by the way, is it increasing its potential energy as the universe expands and the galaxies are farther and farther from each other? So it's a profound question. There's also a quantity called momentum, and some of you know what momentum is, but let me remind you, momentum is the mass of an object times its velocity. It's actually a vector, mass times velocity. Notice the difference between momentum and kinetic energy. Kinetic energy is 1/2 mass times velocity squared, but momentum is just mass times velocity, kilograms, meters per second. And it's extraordinarily profound that momentum is always conserved. If you have a box and any kind of crazy circus-like behavior occurs inside that container, the amount of momentum in that box initially is equal to the amount of momentum at any later time. You can't create momentum, and you can't destroy momentum. So the mass times the velocity of all the parts of a system stay the same. And it's especially true when objects collide with each other and deliver momentum from one object to another. So a good example of this is if you are at a pool table and you hit one ball, it has momentum, m times v, and when it hits the other ball, often it's the other ball that takes that momentum now. So one ball has momentum, gives it to the other ball. Momentum has to be conserved, And the best place to do these experiments about momentum are in a place where there's no friction at all. Because friction, of course, causes things to slow down, and the momentum and the energy gets transferred to whatever it is that's causing the friction, like the floor. So if you're going to do a good physics experiment, what you should do is go into, that guy made that video in his garage, as far as I can tell. And he's must be about 58 years old because of the music. And just to summarize, let me give you a quiz. So get your colored pieces of paper out. Here's your quiz question about momentum and momentum conservation. Ready? Suppose you have two trucks. One is boogieing along at 40 kilometers an hour, and it hits another truck. They're on an icy road, the idea being that there's no friction. Before the collision, one of the trucks is at rest, and actually I have these backwards. So it's this truck that's at rest, that one's moving. So truck number 1 is the one that's moving, and truck number 2 is the one that's stationary. Truck number 1 here is coming at 40 kilometers per hour. And the question is, after the collision between the two trucks, let's assume that the trucks bashed into each other and stuck together because they damaged each other. Suppose the two trucks stick together. They're equal, identical trucks. So now you have the pair of trucks acting like one object. And the question is, what is their final velocity after the collision? And your answers are 10 kilometers per hour, 20 kilometers per hour, 40 kilometers per hour, and 80 kilometers per hour. I'm going to give it a little bit of thought. Well, okay, show me your answers. I see a lot of B's. That's all I see are B's. There's a C. I see some C's. Well, here's the way I would work out this problem. I'm going to do it in my head and talk out loud. I guess I'm always talking out loud. I'm going to think out loud. And then I'm going to show you on a slide how to work it out. I like to work it out in my head because then I can sort of feel what the relevant physical issues are, and then work it out with an equation and see if the equation agrees with my logic, with my intuition, with my reasoning. So my off-the-cuff mental approach would be that you have two identical trucks. One is going at 40 kilometers per hour. When the two trucks smash into each other and move together, they have twice as much mass. And so in order to conserve momentum, this new object, the combined pair of trucks, has twice as much mass, and in order for it to have the same momentum that the original truck did all by itself, that pair of trucks has twice the mass, so it better have half the velocity, so that the product, when I multiply the mass of the two trucks times their new velocity, that product is the same as what the mass times velocity was, the momentum was, of the original truck. So I think two trucks with twice the mass must be going at half the speed of the original truck. In other words, my guess is 20 kilometers per hour. And if you wanted to work this out with algebra, it's pretty easy. Two trucks of equal mass. Before the collision, one of the trucks is at rest, the other one is moving. And so originally, truck number 1 has a mass times a velocity that's 0 because it's not moving. The other truck has a mass times a velocity that's whatever its mass is times 40 kilometers a second. So that's the total momentum in the box. And now if I consider what happens after collision, they have twice the mass because the two trucks stick together. And so we want to know what that final velocity is, and you could solve for it with algebra. You simply say from momentum conservation, the final momentum is the sum of the two momenta originally. That is to say, the final momentum is the sum of the momentum of the original truck number 1 and truck number 2, one of which had 0 momentum. And so we already worked out that there's 40 kilometers per hour times the mass here. And so there it is, mass times 40. And there's twice the mass for the truck now because there's really 2 trucks there. And we can solve for the final velocity. And so solving for the final velocity, divide both sides of the equation by 2, and you get 20 kilometers per hour. Notice that the mass cancels out on both sides of the equation. So the final answer is 20 kilometers per hour. Now, there's one last quantity I want to talk about today, and that's called not momentum, but angular momentum. It too is conserved always, always, always. Any kind of process in the universe, angular momentum is conserved. What is angular momentum? Well, as the name implies, it's like the momentum, mass times velocity, but it's the mass times the velocity going around in some circular motion or spin. So angular momentum is the momentum of rotation or spin. Here's a picture of a mass moving around in a circle a distance r from the center. And as that mass goes around, it has a certain angular momentum because it's the momentum of circular motion. And it turns out that the amount of that angular momentum is always conserved in any system. I'm not even going to show you the equation for it because that doesn't matter. But you can remember that you've seen angular momentum conserved in many places of your life. One is at the ice skating rink. If an ice skater has her arms out, the ice skater is twirling around slowly, but when she brings her arms in, she spins much more rapidly. And so just by virtue of conservation of angular momentum, not doing any work or exerting any torques or forces, just by pulling your arms in and conserving angular momentum, you go faster. You have the same angular momentum that you had before. The difference is the radius, the distance from the center of your body to the masses is less when you pull your arms in. And so there's some amazing conservation laws in nature. I don't know why nature has these conservation laws, but one of them is a conservation of mass. The amount of mass never changes. The amount of energy never changes. Momentum and angular momentum. Those 4 quantities never change in a closed system, kind of. I'm lying a little bit here, so let me tell you how I'm cheating. I already told you that mass and energy are 2 forms of the same thing, and only Einstein figured this out by E equals mc squared. So really, it's mass and energy together that are conserved, but for all intents and purposes in your daily life, mass is conserved separately and energy is conserved separately. Only when there's a nuclear reaction does mass get converted into energy. And so from the standpoint of chemistry, whenever there's a chemical reaction, like 2 hydrogen molecules combining with an oxygen molecule, notice that you conserve the number of atoms and indeed the mass of the system. Originally and finally, the amount of mass stays the same. So that's a very profound aspect of your daily life. And the only exception to that, as I said, comes from nuclear reactions where you can convert mass into energy, and that's something that we're going to talk about in Chapter 10 when we talk about how the sun powers itself by nuclear reactions. So I'll stop there. Good luck with your homework tomorrow.